Welcome back to Casey Science Hub, episode 4, Marvelous Mark
Episode
2025.
5.
Episode 5.
Let's go, guys. So, there it is. Pause the video, check out the problem, and then follow up what we've done. Let's go. So, the isotope sodium 24 is radioactive. A sample of solution containing sodium 24 is used to estimate the volume of blood in a patient. The half-life of the isotope is 15 hours. The initial activity of the isotope is 200 becquerels. When it was injected into the bloodstream of the patient, after 30 hours, 1 cm cube of the patient's blood had an activity of this estimated volume of blood in the patient. Okay, guys, this is a very, very simple problem, but you really have to understand what is happening. So normally, the radioactive sample has a half-life or has an activity of 200 becquerels. Okay, now we're going to inject it into a patient's body, and we're going to assume that all of this radioactive substance is picked up by all the hemoglobin molecules in your body. So think about hemoglobin like the smallest uh, unit of blood volume in your body. Okay, so many hemoglobin molecules put together make up maybe a unit volume of blood in your body. So you're thinking of hemoglobin like the smallest unit of measuring volume of blood. Now, if all the hemoglobin molecules pick up this radioactive substance, what is really happening is, hey, after 30 hours, because you injected into the bloodstream, and then after 30 hours, you collect 1 cm cube. Now, after 30 hours, all the volume of blood in your body has picked up the radioactive substance. And so the entire volume is going to have an activity, all right? And the activity there is simply going to be what? It's simply going to be a quarter. Remember that half-life is the time taken for the activity of a reactive substance to drop to half its original value. So this is the original value before it was injected in your bloodstream. And 30 hours later, which is 2 times the half-life of the sample, notice that the activity must have dropped to what? To 4, by a factor of 4. So 200 divided by 4 gives you 50. And so that will be the activity at the moment when the doctor is about to remove 1 cm cube of blood from the patient. Now, if I take out just 1 cm cube of blood, the activity again reduces. Why? Because activity is a function of what? Number of radioactive substance that is available in the radioactive sample. So let's just do some math here. Of course, the activity is lambda n. Lambda is a decay constant. N is the number of particles that are available in that sample. Okay. So you realize that I can find the number of particles that are available to decay by simply doing what? Giving volume over molar volume multiplied by La. This is how you get number of moles now, multiplied by La, and that gives you number of particles now. And so you could also get it by giving mass over molar mass divided by La. But now we want to use giving volume over molar volume. Now this molar volume is really, it does not matter. Why? Because we don't know. Are you doing this experiment at STP, at RTP? We really don't know anything. All right, so we'll just keep that molar volume there at some molar volume Vm. Now that's our equation one, right? So A final will be lambda. Lambda is unchanged, okay, because it's just linked to one half, T half, that's not changing. And then we have V2 over Vm times La, okay? Now, if I divide equation one by equation two, I'm going to get A0 over A final to be equals to V1 over V2. So my V1 is going to be A0 over A final multiplied by V2. What's my V1? My V1 is the volume of blood that is present in the patient's body. Okay? Because when the volume of blood in the patient's body is V1, the activity is A0, and it's simply a quarter of this because, hey, I've injected and I spent 30 minutes in your body, so all the hemoglobin molecules have picked up it, all right? And that's how I can estimate the volume of blood in your body. So, yeah, that's really what is happening here. And then my V2 here is the sample volume that you picked up, and that's 1 cm cube, okay? And then the activity there was simply 8.3 times 10 to the negative 3 becquerels. All right, so there you go. We can get our V1 as what? Our V2 is, or our A0 is 50 becquerels, okay? And then our A final is 8.3 times 10 to the negative 3. And then, of course, our V2 is the sample volume that the doctor collected, which is 1 cm cube. And in liters, that's 1 times 10 to the negative 3 liters. So that's about 6.0 liters of blood that is available in your body. That's really easy, right? Because, yeah, it's really easy. Uh, So the next part of the question says, state the observations from Rutherford's alpha particle scattering experiment and the corresponding conclusions that were drawn about the atom from each of them in a tabular form. So this is it right here, guys. So observation, most of the alpha particles go through undeflected. Conclusion, an atom is largely made of empty space. Okay, a few of the alpha particles were deflected through small angles. Conclusion, the positive charge in an atom occupies a tiny space. Okay, again, yeah, that's really just it. Like these things, you sing them in physics and also in chemistry, so there's really no point going through every one of them. But it's there for you guys to read. Thank you so much for checking this one out. Let's move on to the next episode.